Meanwhile, we can test probably the presentation.
Yeah, sir. You please open, sir.
Can you see the title screen?
Yes, sir. Yes, sir. Wave for 5G wireless communications.
Thank you.
Thank you, sir. And that introduction, that is the first slide you used the logo of Kakatiya University. Happy to see that.
Me too.
Yeah, sir. Sir, you can continue, sir, because meanwhile the participants will join. Mostly 25 to 30 members total participants. Okay. Yeah, sir.
Okay. So with your permission, I am starting today's lecture.
Yes, sir.
I am very honored to be invited by Professor Hari Krishna, and he gave me a chance to speak in their ATAL FDP course, Challenges in Capstone of 5G and AI. The topic of the course is very interesting and it is very relevant. So I am very happy to be a part of this. Now, the topic that I'm going to talk about today is millimeter wave for 5G wireless communication. 5G is a very big concept, and people view 5G from different aspects. Like if you are from an electrical background, you view something different. If you are a communication engineer, you view something else. And if you are a computer science expert, then probably you view something else. So these are some, I should say, part perspective, and I want to show my part perspective as well. Like millimeter wave is not exactly the overall 5G. It is only a part, but it is going to be a very important part, not only in 5G, but also in beyond 5G communication as well. Because what we consider as of now, that 5G has been rolled in many places, but millimeter wave is still penetrating. So probably in coming 5 or 10 years, the role of millimeter wave in 5G and beyond 5G communication will be even more or even higher. So we just go through some ideas of 5G that people have, and the scope of 5G that probably will be, and how it will be changing people's lives. So I'm just going to the first slide, and I think this is my introduction. So already Professor Hari Krishna has said this, so I'll skip this. So I'll just go to my first slide and tell you about the huge applications that 5G can have. On this slide, I am showing two pictures. On the left-hand side, I am showing a possible telemedicine application of 5G, which is now a reality. And although I am showing an animation on the left-hand side, that animation has been already realized in China and many other countries, where the robotic arms are doing microsurgeries, where the doctor is present thousands of kilometers away. So it is possible with 5G, the huge bandwidth and huge capacity of 5G, that you can do remote surgery. And to my view, doing remote surgery is probably one of the highest achievements one can have in the communication domain, because it requires precision, it deals with living human beings, and it is very crucial for patients. So that is kind of very serious application of 5G, which I show on the left-hand side. On the right-hand side, I show a somehow not so serious, but again, very much bandwidth consuming application. The right-hand side shows a picture of Professor Misha Dollar. Professor Misha Dollar is a professor in the University College London, and he did the first 5G concert, where you can see probably a girl on the right-hand side. She is actually Professor Misha Dollar's daughter, who was in Germany. And during the concert, the daughter performed from Germany in front of Brandenburg Gate. On the other hand, the Professor Misha Dollar was in Albert Hall in UK, and they performed in sync. So it shows that the telepresence, the live concert, all these things are possible with 5G. Although the two people can be, or many people together can form a band, although the band members are thousands of kilometers apart. If you're interested, I will share the slides, and there's a link in below where you can see the YouTube video as well. It is very enriching to see how like telepresence has been already realized. The video is around 1 year old, so already 5G has got its full potential. So this is one side of the picture where 5G is showing tremendous promise, and 5G is probably showing tremendous capabilities. But on the other side of the coin, there are still some perceptions, some hesitations, and there are some ignorance in the common people domain, which probably is very worrisome. And I want to show those things in the next slide. Well, probably all of us are here attending this webinar due to the coronavirus, and I would have loved to probably address you in a face-to-face manner. But even people try to relate 5G with coronavirus as well. Like there had been a widespread rumor that 5G waves are causing coronavirus and so on. So I'm just trying to show with a little cartoon on the right-hand side that suppose there is an extraterrestrial intelligent person who is trying to see how much human have progressed, and when the ET sees that people are still believing such kind of conspiracy theories, he gets dejected. So this is to give you an idea like how people perceive 5G. On some people think that it is tremendously promising and the experience will be much rich, which is true. On the other hand, people have some misconceptions. I tell you, the misconception was so wide that IEEE, which is the biggest organization in the electrical and electronics domain, had to issue a specific order showing that 5G does not cause coronavirus. So you can understand the level of panic and other kind of things that are associated with 5G. So with this, I probably set the tone to 5G, what 5G can do and what 5G cannot. And then probably let me tell you a little about the 5G status. First, I will be talking about the 5G status all around the world. And then as we are all belong to India, probably I will be focusing on how 5G is relevant in India. That is, what is the status of 5G in India. Fortunately, I have been a part of some of the standardization bodies, so probably I can give you the status as well. So this is my total lecture, which is divided into 3 parts. In the beginning, I will be talking a little bit about 5G to set the tone, and then I will be introducing the term millimeter wave. Millimeter wave may be known to many of you, may not be known to you, so I'll just go through the basics. There is no harm in going through the basics again if you know it. And then I will try to combine both the concepts like 5G, millimeter wave, after introducing how 5G is going to use millimeter wave and why we are so keen in introducing millimeter wave for 5G. So as I was saying that let us try to first assess the status of 5G worldwide. Well, I start with a slide from Qualcomm. Qualcomm is the company that is behind CDMA revolution. And many of you probably have used CDMA phones when Reliance or Sham has launched their CDMA services. So Qualcomm is a world leader, and Qualcomm is obviously assessing the telecom scenario continuously. So this one has been taken from their company white paper slide. And they are showing that already 45 operators worldwide have launched 5G. So you can see those white and light white points on the globe that where 5G has been already launched. And there are, by operators, we mean the operators like Vodafone, AirTel, these like things, but I am not specifically targeting them. I'm just talking about worldwide operators. And there are 40 plus OEMs. OEM stands for original equipment manufacturers. These include Nokia or Samsung or Oppo or Vivo or something like that. So more than 40 companies have already launched their 5G phones. And what is more important is that more than 340 operators in 115 countries, they are investing on 5G. That means either they are in the trial run process, they are doing the field test, or they have already launched the network, but it is not open to the public at various stages. So this is the situation overall around the world. So that means 5G is already here. So it's not about like whether we are going to take 5G or not. 5G is here, so it's probably the question that we should ask ourselves, like how we are going to adopt 5G for us. 5G is going come already here and it's going to stay. Now, if you are interested in some real-time map, like if you want to study how the 5G is evolving over time from day to day or month to month, there is a nice map which I present next. This is the latest map from October, and you can get it in worldtimezone.com, which shows the actual implementation of 5G all over the world. And there are different color codes, like the green ones are yet to go for 5G, which are happy with either 3G or 4G services. That includes vast part of Africa and Canada as well. On the other hand, the 5G research and development is taking place quite well in Brazil, in India, in Saudi Arabia, in South Africa, and so on, and many East European countries. And there are 5G implementations which are having trials. Trials are already being done in China, in Russia, in US, and there are some cities, the metropolitan cities in Europe and US and China and many other places where the 5G is already available in a commercial version. That means you can buy a 5G SIM, you can buy a 5G phone, and you can enjoy the 5G services. Of course, with time, this thing will evolve and this graph will change its color. So if you're interested in tracking how 5G is evolving, you can check this graph from time to time. So there has been a lot of discussion about what is 5G around the world. Let us now zoom on our own dear country, India. Like, what is the status in India? From this map, at least we can see that there are 5G research going on, but what is the status and how far we are in the world seat? Well, before I start discussing on the status of 5G in India, let me tell you one thing, like in wireless communication, we are somehow fortunate, because you see, when we had landline telephones, we are far, far behind compared to the developed countries. The tele density, which is the number of users per 100 customer, was less than 2% in India, when it has already reached more than 60-70% in developed countries. But that was the landline telecom domain. When the wireless has emerged, we readily jumped from no phone to wireless phone. Like, many people who had their first phone was the wireless phone. So that was a big leap for us, and that's why we probably could skip some of the development cycles. The developed countries already had a big landline infrastructure, so they struggled to adopt new technologies. And the same thing also happens in case of 3G or 4G or something like that, because you can see that 4G has been widely invested in many European and US countries, US cities. So when they are going to have 5G, that means 5G means new mobile towers, new mobile phones, new mobile SIMs, and people are not very happy to go for or investing a lot of money. But in India, we enjoy the cheapest services, so probably it is easier for us to migrate. The point of discussion is, or it means that we are not in a backseat now, and we have already caught up with the world. And fortunately, the standardization bodies are also in motion. So earlier, it was always some US or European companies, or maybe some Chinese or even Korean companies who were dictating the world scenario. But now we have our own say. And due to the big customer base, probably they cannot ignore our voice as well. So I will be talking about some of these interesting developments in the next slide. Okay. So my next slide is about 5G in India. Well, the timeline has two major entries in the slide, in 2018 and in 2019. In 2018, there was a high-level forum report from government which assessed how much we are ready for 5G, and that report is available over internet. And in 2019, there was again another big leap. I was talking about the world should hear our voice, and the world heard our voice. Actually, that is a society in India that is called Telecommunication Standards Development Society India, or TSDSI. TSDSI is one endeavor of Department of Telecom, and they are going to be vocal repetitively in various world forums. There are some world forums. For example, the most famous of them is WRF, or Wireless Research Forum, which generally is held after every 4 years. It's something like Olympic of wireless. And in these, it last held in 2019 in Egypt, near Egypt actually, in Marsala. And there we had Indian delegation. And these conferences are very important because here people decide on the standards, like what 5G will be, whether Indian companies will have some say on that. Now, what we achieved in the global circle was we have made our case with LMLC, low mobility large cell. To make you understand about this idea, let me first name few persons who are behind this. There is a very famous academician, Abhay Karandikar from IIT Bombay, who is now heading IIT Kanpur, and IIT Madras director. Fortunately, they are all from this wireless domain. So it's a very fortunate era. We are having all the IIT directors almost, they are having some connection with 5G or wireless, and they are working together. And they together, along with some other professors in IIT Hyderabad, like Kiran Kuchi, then Radhakrishna Ganti from IIT Madras, they all went there to present our case. And our case is quite different from the developed cases. You see, when a European country wants to talk about 5G, they are more interested in having wide broadband access while they are traveling in a high-speed train. If you go in France, they have an average speed of 250 to 300 kilometers per hour, the SNCF trains, which are one of the fastest on the wheels. So obviously, when France becomes vocal, they want their customers satisfaction in moving trains, and they should have like Gbps connectivity or gigabyte per second connectivity in train. But in India, we are not very much interested in like very high speed, high broadband communication. Rather, we are interested in large rural areas, which can be probably served by one tower in e-panchayat or that kind of schemes. And probably people have very low mobility in the rural areas. They either move by walking, or they probably use the bicycles. So the mobility is very much restricted in India. They have not very high speed, but the area that should be covered, that must be large, and the number of subscribers that has to be catered is large as well, which is completely opposite to what happens in developed countries. They have very sparse population, very few population, but they have very high mobility. So fortunately, now LMLC is a part of 5G standard, and this is how we are making our voice heard in the World Forum as well. So this is somehow the background of how 5G is doing in India. And let me now talk a little bit about what the TRAI, Telecom Regulatory Authority of India, I hope you know about TRAI. The TRAI is repetitively giving some orders for frequency use and so on. So they are having a hybrid kind of plan for 5G in India. They are thinking that probably we should be requiring very high-speed connectivity in some urban centers, like in metropolitan cities. But like there is a shopping mall in Chennai, for example. Obviously, there will be many people, and they will be asking for very high data rate. So those are some hotspots in metropolitan cities which require very high data rate, where they can use the high band, because high band supports high data rate. And then they can have a mid band, which is lower than 6 gigahertz. It is between the current cell phone frequencies and the Wi-Fi band frequencies. So they are going to cover the whole metro with the mid-band frequencies. And then they can have a low band, which are the white TV space bands, which were unused, and probably they can have a nationwide or maybe a statewide kind of metro. So this is what 5G in India is about. And then I briefly talk about how this whole thing evolved and how 5G is different from 4G. Well, over the time, the generations evolved from 2G to 3G to 4G to 5G. And although I am showing a number in the year like 1991 or 1998, there is no point of thinking that it exactly evolved in this year. It is a very continuous process, and it is continuously evolving. And you cannot probably say exactly when 5G is being launched. So it's a continuous improvement over the network. Like when 4G networks was first launched, we had LTE. LTE was not exactly 4G. It was like 3.75G or 3.9G, if you want to say so. And when LTE Advanced A version 10 came, then only you can probably say it is truly 4G, because that's what the standardization bodies have defined. So it is a very continuous process. The point is, it is a very continuous process, and it's going on and on. Now, let us try to understand what are the fundamental difference over the generations. The 2G was the first digital generation, which provided not only voice calls, but also SMS-based text. And in 3G, we had fast of our smartphones. So not only text, but also internet connectivity that was there. But the interconnectivity was kind of poor. Like you probably can only download ringtones. You can probably only surf the operator websites and make only emails on text-based kind of thing. In 4G, we had true internet experience where we can download videos, we can have video calls and so on. And in 5G, probably not only this, we are going to have, say, 3D holographic projection, just like what I have shown with Professor Misha Dollar and his daughter. So we can have a 3D video call, we can have smart home and this kind of wide applications where we are going to connect a lot of Internet of Things devices with our mobile phone. And as 4G is still here and 5G is rolling out, it is very important to understand the difference, fundamental difference between 4G and 5G as well. There are certain regions which the standardization bodies define that what 5G should be like. The first one is latency. Latency is the end-to-end delay in delivering a packet. The delay in 4G was around 10 milliseconds. It should be less than 1 millisecond in 5G. The data rate, which is probably the most important thing a subscriber thinks about a mobile network right now, it was something like 1 Gbps in 4G, which should be more than 20 Gbps in 5G. And obviously the spectrum, that is the bandwidth that is available, was much lesser in 4G, but that should be much more in 5G. And this is where the whole topic is concentrated about, like how we can manage this available spectrum. If we're trying a 30 gigahertz spectrum, where to get that from? So that's why this topic is important, millimeter wave for 5G. And of course, there are a lot of more nodes. Like earlier, we had only 5 phones. Now we have our smartwatch, a pacemaker installed on our body, which is connected to the body area network. We might have a smart TV, we have a smart fridge, smart washing machine, and whatnot. So all these things are going to be nodes and which are going to be 5G connected in recent future. So this is 5G in a nutshell and how it is different from 4G. And let me try to finish this first part of the talk by talking about the use cases. There are 3 major use cases of 5G. The first one is EMBB, or that stands for Enhanced Mobile Broadband. The second stands for MMTC, which is Massive Machine Type Communication. And the third one is URLLC, which is Ultra Reliable Low Latency Communication. Now, these 3 are 3 different use cases which are envisioned for 3 different applications. Enhanced Mobile Broadband is for users where if you have enhanced mobile broadband, that means you have more data rate. So you can probably now have those 3D kind of holographic video calls and HD video calling and probably real-time online massive gaming and whatnot. So that's the user part. On the other hand, MMTC is Massive Machine Type Communication, where there are a lot of nodes involved. It might be the case for the automatic vehicles, which are a talk of the town now. We are going to have driverless cars soon, and there are already driverless cars in Los Angeles and in some Korean cities where you can hire a driverless car. So if there are driverless cars moving in a city, there will be probably thousands or millions of them, and they should communicate among themselves so that they can travel smoothly. So these are machines which are going to talk with each other. So we have massive machine type communication. And the third one is URLLC, which is more related to the industry. This is ultra reliable and low latency. That means there is no scope of failure. The packet should be delivered with say 99.999999% of reliability, and there should be low latency. That means whenever you send the packet, it should be received immediately. Now, these are something which are required for, suppose, robotic surgery. If you are transmitting data and you are asking the robotic arm to move, you want exact precision. There is no scope of error. Even a scope error of 0.01% can take one person's life. So in these cases, there is no chance of error, and it should be transmitted immediately. Now, suppose the robotic person is doing surgery and you have a network blockage and you cannot send the commands, then of course it will be fatal. So these are some areas where 5G are going to be used. And the final slide of the first part of the talk is about the standards, like how the standards are evolving and what is the timeline. That means what we are going to see in next 1 or 2 years. I do not know what we are going to see in next 5 or 10 years, because nobody can predict, and most of the predictions went wrong. So what we are going to say, that what is currently in development and what is currently planned, and probably this will go like this. So let me introduce you to some bodies which are working on 5G. First of all, there is ITU. ITU stands for International Telecommunication Union. This is basically a wing of United Nations. I hope everybody knows about United Nations. United Nations is the group of is an organization which is a group of countries to maintain peace and harmony and avoid political conflict all over the world. And they have a mission that interoperability is there. Like, people can move freely, people can communicate freely. So they have established ITU, International Telecommunication Union, which looks after that the same standard is followed everywhere in the world, so that people, when a person buys a phone in Sweden, he can talk on that phone in Uganda, and he probably can buy a SIM in India as well. So ITU actually does not define the standard directly. They give some vision, and their vision is IMT 2020, which is International Mobile Telecommunication 2020. And they set a series of specific goals, like if you are going to have a standard for 5G, what should the standard achieve? So the IMT 2020, if you read through them, it will give you some vision or capabilities, like these capabilities should be there. But how the capabilities should be reached, ITU generally does not specify that. That is the duty of the standardization bodies, like the 5G or 3GPP. 3GPP is third generation partnership project, which started working right from 3G. You probably know that there was a big war between GSM and CDMA. We had like AirTel and Vodafone kind of SIM, and then some people used the Reliance kind of SIM, CDMA. So there was a big war, like whether you should use GSM or CDMA. And while the war was going on, there was some activities to reconciliate these two domains, and that's how 3GPP formed, third generation partnership project. The third generation partnership project, although it was formed in Europe and had some partners in US, but ultimately they span the world. So what the 3GPP does, the 3GPP is actually developing the 5G standard, and they have got the release 16, and they are going to have release 17 in 2020. Probably the plans has been delayed due to this pandemic. On the other hand, I am just showing with this third arrow that what IMT 2020 was. IMT 2020 was announced in WRC, which is Wireless Radio Communication Consortium conference, and they are having the specifications. So 3GPP follows those specifications. Then there is the 5G group as well, which has come up with 5G new radio. They have this release 15 trials, and the release 15 are being launched now in 2020. Like, there is a small company in Turin, Italy. They have got their own network with this 3GPP R15 release, and the 3GPP R16 probably will be launched in 2021. So on one hand, the standards are being developed, R16, R17, and on the other hand, a bit delayed, the standards are being implemented. Like R15 is being implemented now, and R16 probably will be launched in the next year by the mobile operators. And at the bottom, I show that the 4G is not dead. The 4G is going to stay here for as well. Like, still you probably have your 2G phone, some of you, and probably most of you have 3G phones. Like I have a 3G phone. So those things are going to stay, and 4G is going to stay for some time. And to my view, it is at least going to stay for the next 5 to 10 years with backward compatibility. So with this, actually, I finish my first part of discussion. And if there is any questions, or if you have any queries, I'll be very happy to answer that. I'm just taking a 1 or 2 minute break and want to ask your opinion about how it is going on. Come on, let us make it interactive a little bit. Or if you want to write, you can write in the chat box as well. I can see the chat box. I can see Naveen Kumar is typing something, so maybe it will be visible in chat box. Anybody else having any queries till now?
Nothing.
Or is there any topic I should explain once again, or probably go in a bit detail? Nothing of that sort? Okay. So I don't think any queries are there. So maybe I can continue with my presentation. And okay, fine. So I have got one query that's nice to have. So Shiva Martha is asking that what is the difference between millimeter wave and massive MIMO? Well, I will be talking about millimeter wave, and I will be talking about a little bit about massive MIMO as well. So I guess I will be answering your question down the line. But let me tell you that millimeter wave is a wideband technology. It's like using the frequencies in the millimeter wave range, which I will just explain. On the other hand, the MIMO is using multiple antennas, and massive MIMO is using massive number of antennas, both at the transmitter and in the receiver. And actually, these two technologies are not competitive in nature. Rather, they are complementary, because we can show that with millimeter wave, the size of the antenna reduce a lot, and it helps to put multiple antennas in the transmitter side as well as in the receiver side. So it's like if you want massive MIMO, probably you have to go in the millimeter wave. So it's like merging or marriage of the two technologies. So with this, that was a nice introduction, and that's with this probably we can just go back to what we were doing, like presenting the slides. Okay, so yes, anything else? No, I guess. Okay, so I have got another chat. Okay, fine. So let us go back to our slides once again, and let us go to the second part of our conversation. So I will just present now again my entire screen. Fine. So I hope now you can see the slide once again. Thank you. Okay, so what I was talking about is millimeter wave. So in the next part of our talk, I am going to introduce the millimeter wave. What is millimeter wave? Why there is so much noise all around the world with millimeter wave, and how it is going to change our life. We start with a very basic equation. I guess everybody knows about this equation. This equation is the wave equation. Wave equation is the relationship between speed, frequency, and wavelength. If you consider the speed of any wave, it is basically multiplication of frequency and wavelength. If you consider electromagnetic waves, then the speed of in the wave is 3 into 10 to the power 8 meter per second, which is the speed of the light. So this is probably a very basic equation. Everybody probably knows this, and everybody uses this to teach their students. And you can find the frequencies or wavelengths from this. Obviously, the wave equation will be different in a guided media or in a waveguide or something like that. But in free space, you can probably use this to find the frequency and wavelength. Now, when you put a frequency value in this wave equation as 30 gigahertz, then what lambda value that you get is equal to 10 millimeter. So that's what we are showing in the bottom equation, that is a range. So if you put 30 gigahertz, you get lambda value of 10 millimeter. If you put 300 gigahertz as f, the red f, then the blue notation, which is lambda, what you get is 1 millimeter. So this whole slide tells you the range of the millimeter wave. That is, if you have a frequency between 30 gigahertz to 300 gigahertz, then you have a wavelength between 10 millimeter to 1 millimeter. And these frequencies are known as millimeter wave. So millimeter wave is nothing but talking about the frequencies in terms of the wavelength, where the wavelength of the waves are in the order of millimeter. That's what millimeter wave is. Then why it is so big thing? Because it is so easy to understand and it is probably very trivial. Well, the point is, in cellular mobile communication, we never thought of anything beyond 1 or 2 or something like that gigahertz. When the cell phones were first introduced, we used megahertz frequencies. Like we used 400 or 500 megahertz frequencies. Then we have used 700 megahertz frequencies. And then we have used 800 and 900 megahertz frequencies. And in 2G, we have gone up to 1.8 gigahertz. So what is so important about this millimeter wave is that they are thinking beyond this 1 or 2. If you put in context, the Wi-Fi that we use either uses 2.4 gigahertz or 5 gigahertz. And in contrast, now we are talking about 30 gigahertz. Now when, or probably hundreds of gigahertz. Now when we have hundreds of gigahertz or something like that, then the design of the antenna, the design of the chip, the design of VLSI, everything is probably going to change. So that's why millimeter wave is so big thing nowadays. Well, so let us just formally again define what we described so far. That is, millimeter wave are the range of frequency. Okay, so millimeter wave is the range of frequencies between 30 gigahertz to 300 gigahertz. So and the corresponding wavelength is between 1 millimeter to 10 millimeter, which we define in the next slide. Whatever I have said is just written in plain simple English here, that millimeter wave refers to the portion of electromagnetic spectrum where the wavelengths are between 10 millimeter to 1 millimeter, or in other terms, the frequency is between 30 gigahertz to 300 gigahertz. However, this slide provides you with another picture, and this picture says that although millimeter wave is between 30 gigahertz to 300 gigahertz, we are not going to use the whole frequency band. Rather, there are some frequency chunks which we are going to use for millimeter waves, because these frequency bands are also used by satellites and many other applications. So we are not going to use the whole band for the cellular mobile communication. Rather, we are going to only use some chunks of it. There has not been a global consensus yet to use which chunks, but more or less the same chunks are being used. Like if you consider India is planning to use 28 gigahertz around frequencies. Europe is using 26.5 and US is using around 27. So they're more or less similar in nature. So this is millimeter wave, but the big question is, can it work seamlessly? Like, can we use 30 gigahertz at all? Well, The answer is yes and no at the same time. Yes, because it has been already shown many years ago that millimeter wave works. This is a picture of Professor J.C. Bose, and I was very proud to see this picture last year, last year, when I attended a conference in Portugal, Lisbon, where one IEEE fellow professor was showing his picture and saying that he is the pioneering of millimeter wave. Like when we fight over who invented radio, I hope people who are participating in this webinar have some introduction to electronics and communication. So probably you know that there is a fight behind who invented radio, and people say that it is Marconi. US people say that. If you go to Germany, the German people will say that Heinrich Hertz did that, and if you go to Russia, the people say that Alexander Popov invented radio. And when you come to India, we Indians are very proud to say that Professor J.C. Bose invented radio. Well, that is a big debate. But what nobody debates is that none of the persons that I have mentioned, neither Marconi nor Hertz nor Alexander Popov, has ever thought of beyond the radio frequencies, like beyond the kilohertz, megahertz kind of frequencies. It was Sir J.C. Bose who thought that we can even transmit the signals at gigahertz. And he was the first in the world to demonstrate a millimeter wave. And he demonstrated it in 1897, that is 120 years ago, in Royal Society, UK. So in front of the learned audience in United Kingdom, he showed that he can generate, just imagine the type of hardware probably he might have at that time. He made his own hardware, and he showed that a short range transmission is possible with 5 millimeter wavelength. And he actually used some gunpowder to transmit that kind of thing. So that's pretty impressive. Now that means the millimeter wave is nothing like completely new. It has not emerged in 2020, or it has not been there from 2010. It was always there, and millimeter wave was always being used for space and military domains. There were satellites being used. The military people use the millimeter wave. So why I question that whether it works or not? The right question is, well, it worked for satellite, it worked for military. Does it work for normal cellular mobile phones? Why it is important? Because when you put in normal cellular mobile phone, the number of subscribers is huge. If you're considering satellites, there are only few satellites. If you consider the total number of satellites the Earth is having, it will be 1,500. The communication satellites. I'm not talking about spy or weather satellites. If you are considering communication satellites, it will be less than 1,500. So very few people, very few satellites. If you consider military, how many people in the military are using military communication? Thousands maximum at the same time. But when you consider cellular mobile used by people, there will be billions of people. So can we have a system which can work for billions of people in probably thousands of environments? That is the big question. And that question actually was asked many times, and it hindered the proliferation of millimeter wave. The technology was not mature. We didn't have good antennas. We didn't have good VLSI. We didn't have a good front end. But now people are developing those high-speed antennas, high-speed front end, high-speed chips, and it seems that within very few years we are going to have millimeter wave. And there had been trials all around the world. There had been other things. But let me tell you, like, what was the big challenge in millimeter wave? Well, why people are so hesitant in going from 1 gigahertz to 30 gigahertz? What is the big deal? The big deal is the wavelength or the frequency. You see here with this cartoon, I'm trying to show you what happens with waves which have shorter wavelength. If suppose you are inside a room and the room has a wooden door, and you lock the wooden door and then shout from the other side of the wooden door, still probably if you are standing on the outside of the wooden door, you can hear some of the voice. But if you light a torch, the torch light does not reach the other end of the door. The point is, when you have a voice which is having much shorter frequency and larger wavelength, then it can bend around the obstacles. But on the other hand, when you have light, it has much shorter wavelength and much higher frequency, and even small objects can act as a barrier. So this tells you the whole story, that when we use 1 gigahertz, even if the mobile tower is 1 kilometer away from us, we can still receive a good signal. But if you have a 30 gigahertz transmission and millimeter wave, then we cannot receive signal with our mobile phone. So we need towers in a very short range. That means we require towers in a very nearby domain. So these things are issues when we think about millimeter wave, and this caused multiple researchers to work around the world. And there is a group in okay, I'll show you this. There is a group in USA which is the pioneer of millimeter wave. They are the group of Theodore Rappaport. The Rappaport, if some of you read the wireless communication, there is a famous book by wireless communication by Rappaport. So Rappaport is the man behind. He is known as godfather of wireless in US. So he is doing the experiment here and showing that actually millimeter wave transmission can take place even in a remote setting where you have complex geographical terrains with lots of vegetation, trees, and boundaries and so on. And this is actually near a field near Rappaport's home. So they have shown that it does work. So let me just summarize the challenge once more. Like, what is the big deal? Like, why millimeter wave was not still being used like 5 years ago? This diagram actually shows the coverage area with frequency. The green one is showing the coverage area that you can have with a mobile tower when you're using 700 megahertz signal. The 700 megahertz signal can go up to tens of kilometers. So you can have a quite big area. That means you can only set up a tower and you can reach up to several kilometers. When you use 2.1 gigahertz, which is 2100 megahertz, then the radius shrinks, but it is still on the order of 4 kilometers. So that is the frequency where the 2G operates or 3G operates. So that's still pretty big. But when you go for 28 gigahertz, which the 5G millimeter wave is planning, then the cell radius becomes the purple dot, which is only having a radius of 150 meter. Yes, 150 meter. 150 meter means if you are considering in locality around you, probably you should have 5 towers in your locality to serve the whole locality. Forget about the whole city or whole town. So of course, in millimeter wave, you require many more towers, you require much more infrastructure, and that's what probably people was fearing. But now with the millimeter wave advantages, people are overcoming these challenges. So I will be talking about these advantages after a few slides. Just let me continue with the challenges. Like, what was the big challenge in millimeter wave, and what are the new things that you should think when you are going to use millimeter wave? Well, another challenge with millimeter wave is the antenna. Well, when antennas are working in a higher frequency range, they are going to have narrow beam width. Beam width is how much the antenna can see or how much the antenna can cover. And if you are going for a very low frequency antenna, then the low frequency antenna can cover a very wide range. But a high frequency antenna, because you need the gain, so you have to restrict the beam width. So in summary, if you are going for a 30 gigahertz antenna, the antenna can only see a very narrow area. And if you are in that region, you can receive the reception. If you are outside that narrow region, you cannot receive it. So antennas in millimeter wave are very directional. And if you want to cover all the areas, probably you have to implement a lot of antennas, each covering a very narrow angular sector. So that is again another big challenge with millimeter wave: how to design the antennas, how to design the coverage area, how multiple antennas can cover a very big area, and how to work them together. But at the same time, the millimeter wave antennas are small, so you can probably put a lot of antennas together. So as one of our participants was asking, Harshmita, that what is massive MIMO? So actually the millimeter wave can pave the path to massive MIMO as well, because you can put lots of antennas in the transmitter end, lots of antennas in the receiver end, and you can realize a massive MIMO kind of thing. So what are the challenges in the hardware domain? Let us go back to the slide again. What are the challenges in the hardware domain? Well, there are RF front-end modules which are going to be very difficult in millimeter wave, because you have to make the switch, the amplifier, the RF transmitter receiver, all this hardware to work in the 30 gigahertz range. The packaging of the front end modules, like the packaging on the chip or the motherboard in the mobile, that is also very difficult. Then there is digital signal processing, which needs new technologies. And finally, the semiconductor technology. Well, the current CMOS, which is good for 6 gigahertz, the CMOS might not be that good for 60 gigahertz, or say probably 95 gigahertz. So they are now producing new CMOS chips as well. So here, actually, we again finish our second part, and we again take a little bit of a break and ask you that whether you have any questions about this, because we have introduced what is millimeter wave and what are its challenges, and now probably I'm going to talk about the real stuff, like why then millimeter wave is so important for 5G and why people are so interested. Well, before I invite questions, let me summarize what we have been discussing so far. We had 3 parts of our lecture. The first part was introduction to 5G. The second part was introduction to millimeter wave. In introduction to 5G, we have said that 5G is already here. Like there is no point of ignoring the fact that 5G networks have been launched worldwide. The manufacturers are coming up with 5G phones. The operators are coming up with 5G SIM cards. And you can enjoy 5G network in some of the metro cities, including London, or some of the US, like Washington, DC. So that is 5G. And with world, in India, we are also progressing. And in India, we have got standardization bodies. Our government is forming TSDSI and many other societies to evolve 5G. And then we talked a little bit about how 5G is different from the older generations. 5G is going to give you new services, and that is not going to have only one use case for the users. Rather, it will have multiple use cases, at least 3 use cases. One use case was enhanced mobile broadband, which is the traditional use case for subscribers like us. But there can be machine type communication, which might be for cars, or maybe sensor nodes, maybe some other things. There can be some other aspect, which is ultra reliable low latency, which might be useful for robotic surgery or other kind of things like live concert. And then we went with our second part of the topic, that is introduction to millimeter wave. I mean, introduction to millimeter wave, what we talked about was what is millimeter wave? Well, millimeter wave is nothing but a range of frequencies. And in the range of frequencies between 30 gigahertz to 300 gigahertz. Why then it is called millimeter wave? Because when we are in this band, we have wavelengths in the millimeter wave range. Millimeter wave is nothing new. Professor J.C. Bose have demonstrated it 120 years ago. Millimeter wave is currently being used, but not in mobile, probably mostly in satellite or in space. Why it is not being used in mobile? Because there are challenges. What are the challenges? Well, the number one challenge is the attenuation. When you transmit signal with millimeter wave, the signals attenuate very fast. It cannot penetrate the obstacles. Why it cannot penetrate the obstacles? Well, if I have high frequency signal, then it can travel to a lower distance. To give an analogy, you probably can hear a BBC radio broadcast from all the way from London. But when you have a FM signal, which is having the frequency in the megahertz, the BBC radio signal was kilohertz. But when you have an FM signal, say 98.3 or 97.2, something like that, then you can only hear it in the city, not beyond the city. So if you leave, say, Chennai or Bangalore, and then probably you go to someplace else, or Hyderabad, you move away, and then the FM signal you cannot receive. So this is just an example, like the smaller the wavelength and higher the frequency, the signals cannot reach far. So that is a major point, like the millimeter wave people were hesitant to use. And there are some other challenges like antenna. The antenna has a very narrow beam width, and there are some other challenges in hardware. So this is in summary of what is millimeter wave and what are their challenges. And in the next part of our talk, I'll be talking about why then people are so crazy about millimeter wave, why there is so much research going on. Probably you can understand that research is going on to overcome challenges, but why is the need for overcoming the challenges? Like, can't we do without millimeter wave? The answer is simply no. Well, millimeter wave is going to be an integral part of 5G or beyond 5G. There is no way of denying that. And why so? I will be explaining it now. But before that, if you have any queries, please ask me now.
Hello, good morning, sir. This is Naveen Kumar.
Sure.
My question is, millimeter wave is applicable for indoor communication or outdoor communication?
Okay, a good question.
It is applicable
So
only for indoor environment. It possible in outdoor also.
this is a very good question.
And one more question is, okay.
Yes, the one more question, please.
So one more question is, in millimeter wave communication, whatever the attenuation problem is there, that attenuation problem we can eliminate with the help of beamforming techniques.
Yes. That's very nice way of going through, like having feedback from the participants who are very knowledgeable and going in the right direction. So I feel privileged to address you. Well, first let us go one by one, like the difference between indoor and outdoor. Well, of course, as I said, that the attenuation problem is a big problem with millimeter wave, and with millimeter wave, the indoor communication is almost having not a big problem. But whenever you have outdoor communication or indoor to outdoor penetration, like the mobile tower is outside your home, and you are going to have a mobile phone inside your home, and the tower needs to communicate to your phone, then of course there is a big issue of attenuation. Now the attenuation cannot be overcome just like with other techniques. You can reduce it, but there will be still a lot of attenuation. So there is no way that we can have the towers just like 4G or 3G. We must require a lot of more new towers, so that the towers are more close to the mobile phones in our home. And actually the architecture of 5G is like that only. Like we are going to have small towers, but fortunately when the towers are very close, they need not to be very tall, and you can put like access point like towers. Like if you are using a wireless router in your home, so next generation millimeter wave towers will be like those access points, probably connected to the street lights, probably put on the wall of a tall building and so on. So those will be the new mobile towers. So our idea of mobile towers are going to change. We are going to have access point like of things, and those access points are just like Wi-Fi access points that we have in our home. So maybe the next generation 5G millimeter wave access points will be covering only few homes. And when it is going to cover few homes, then the problem of attenuation is not that much, what I should say, prominent. And it should be like that. Well, this concept of having lot of towers and having a very small coverage area per tower is called small cell. And there are a lot of advantages of small cell kind of things, because with small cell, what we will have is the lesser radiation power as well. Like, so if the tower is near to you, they will not transmit at a very high transmission power, and we will have less radiation. And due to the less radiation, not only health hazards are less, but also the interference problems and other kind of problems are also less. So, and we can have completely new technologies like MU-MIMO or multi-user MIMO or these kind of things. And as Naveen was saying, that we can have along with this beamforming as well. Now, what he is referring here is that if you have multiple antennas, and if each antenna can see only a narrow region, then probably you can have an array of antennas, and you can steer the overall beam of that whole antenna array to your own direction. And this can have a dynamic kind of effect. Like you can track a user, and probably you can form the beam towards the user, and probably this is how you can maximize. This has many interesting applications. One application is less interference, because the tower can beamform to each user, and they can communicate independently of each other, and many other interesting things. So these are some possibilities which I will be explaining in the next part of the lecture. Is there any other question, or Naveen, you want to have some feedback?
Thank you so much.
Okay. So if
nothing. Thank you.
Okay. So is there any other question from any other participant? Okay. I think there's a chat. Nothing actually related to question. So okay. So let me get back to the presentation, and probably I can now talk about, like, if millimeter wave has so many challenges, like why people are so crazy about millimeter wave. So that's the last part of our talk. Okay, somebody has pinged. Okay. Sai Tharun is saying that if there is more tower, there will be latency problem. Well, latency is actually the end-to-end delay. End-to-end delay means if you are going to transmit a packet from a tower to a mobile, then the delay that is required is called latency. So when you consider the latency part between the tower and the mobile, there won't be big issue because the mobile tower is actually closer. However, there might be issues like delivering the packet from the server or the exchange to the many towers. But if we can strengthen our backhaul network, which is the optical fiber network, which is being connected to all these access points, and we can increase the capacity, then there won't be any latency problem. So of course, there is a issue with what Sai Tharun is pointing it, that if there are a lot of such packets and there are a lot of such towers, then everybody is trying to connect to the central server, and there might be a big problem. So it is actually not the problem of the front haul, it is actually the problem of the backhaul. And the backhaul is the connection between the tower and the core network, and that is not wireless, that is actually optical. So it is not a lecture about the backhaul network, but of course the backhaul people are working as well, and they are increasing the capacity of their optical network, and I don't think the latency will be a big issue with their current state. Like just last week I was reading an article that people from UCL in the UK have got an optical fiber which can transmit 1.78 terabits per second per cable. It, in simple terms, it means that there are 1 million Zoom calls per one optical fiber cable. So probably that will be solved. Okay, so let me just go back to what I was talking about. I was talking about, yes, so millimeter wave for 5G. So why people are crazy about millimeter wave? Well, this slide shows an actual performance of an actual 5G network. The actual 5G mobile operator is called EE. There are many other operators as well, like there is Vodafone and O2, and there is also 3 in London. So this test was done in London just before the lockdown started. So I think it is a picture from February 2020. And you can see a person is holding his mobile phone and inside a public bus. And he is running Ookla speed test. Ookla speed test is probably a very common speed test where you can test what is the speed of the network in your mobile phone. And with the Ookla speed test, it is showing 980 Mbps. 980 Mbps is almost 1 Gbps. So that is the amount of data rate the EE Mobile is providing with their 5G services in UK right now. So in some specific areas of London, you can probably realize it. And not only in London, you will probably have it in Seoul, Korea. You will have it in Paris. You will have it in Washington and many other places around the world. So what this slide wants to convey is that the 5G or beyond 5G is about higher data rate. People want high data or high data rate, and people are crazy about this. If you ask a person that why you want a 5G phone, he will say that, okay, I will have 1 Gbps data rate and I can probably download the videos in a quick, and probably I can play more things. I can see the HD videos and so on. So the data rate is a big issue, and this is where there is no other way but to use millimeter wave. Why? For that, I would like to introduce only 1 or 2 equations. These are very basic equations, and if you have gone through digital communication course, then probably you will remember them. If not, probably it's a good point in refreshing them. So I will just introduce the equation that is data rate for noiseless channels, which we generally teach when we discuss the Nyquist rate or Nyquist bandwidth in digital communication. When we discuss Nyquist bandwidth with student, we say something like this. That is, if you have a channel which is having a bandwidth of B, the data rate that we can realize over that channel is 2 into B. This is the theoretical maximum data rate that is possible for a channel. So if you have a channel of bandwidth B, the data rate is 2B. That is theoretical. Ideally, with raised cosine spectrum and other kind of things, it is a bit lesser. But still, it is good enough to give you an idea. But of course, this theorem that we discuss in the class is for binary case. That means we are considering 1 and 0 levels. If you have M-ary case, that means you are transmitting multiple pulse levels, not only 0 and 1, but suppose you transmit 4 pulse levels, like 0, 0, 0, 1, 1, 0, and 1, 1, 4 different pulse levels you transmit. Then probably you can make it double. But whatever it is, it will be still proportional to B. So let us now consider a theoretical case that suppose I want that Gbps connectivity as the 5G promises, and we want 10 Gbps connectivity. And suppose we are ready to go for a very advanced pulse modulation scheme, which is 16 level QAM. Still, the bandwidth that we require is 1.25 gigahertz. So this simple calculation gives you that the bandwidth you require for your intended application is 1.25 gigahertz. Now, when you require a bandwidth of 1.25 gigahertz, what is the problem? The problem is, if you see the spectrum looks like this kind of blue trapezium. And if you want a 1.25 gigahertz of bandwidth, what you need is a difference from the center frequency as 625 megahertz. And when you have this kind of big 625 megahertz distance between center frequency and the end of the band, then you cannot simply slide the trapezium to near 0 frequency. That means in the low frequency range, or when the center frequency is having frequencies less than 6 gigahertz, you cannot simply put it there, because there will be not enough room to put that. And there are already a lot of other applications, like the yellow trapezium shows probably some other applications, which might be for medical, which might be for Bluetooth, which might be for industrial communication, and so on. So those bands are not free, and there is not enough room to put the trapezium. So if you want 10 Gbps data rate, you require 1.25 gigahertz bandwidth, and that spectrum or that bandwidth you are not going to get when you are closing to the baseband or 0 frequency band. Rather, you have to go upward. So you cannot move this way. You have to move that way, like in the higher frequency range. And in the higher frequency range, when you go beyond 6 gigahertz, then only you have enough room to place your spectrum. So the point is, if you want high data rate, you need high bandwidth, and for higher bandwidth, there is no way but to use a high center frequency. That's as simple as it is. And that's why you should move to the 30 gigahertz or probably even beyond 30 gigahertz. Some people are now thinking about terahertz. I do not know when terahertz will be realized, but people have already talking about terahertz. So this is why millimeter wave is required. You require high data rate for 5G. For high data rate, you require high bandwidth. For high bandwidth, you require high central frequency. And high central frequency is only possible when you take your central frequency in the millimeter wave band. So this is a very simple calculation to show you why millimeter wave band is required. But let me go for a more detailed calculation, because the calculation that we have shown in the last few slides was very simplistic, and it was for noiseless channels. Like we were doing it for a very simplistic assumption. For a noisy channel, probably you know that data rate is given by Shannon's capacity theorem. There was a famous person called Shannon who gave some capacity theorem, and the capacity theorem is something like B log to 1 plus S by N. So that's what I am going to show. So if you have a basic course on information theory, we generally teach this equation to all of them. So what is basic Shannon's theorem? The basic Shannon's theorem is data rate should be less than capacity. That is, if you require some data rate, that should be less than or equal to the channel capacity, and channel capacity is given by Shannon-Hartley law, which is nothing but C equal to B log 2 1 plus SNR. The first term is bandwidth. The second term is spectrum efficiency. So the red one is B is bandwidth, and the second one is spectrum efficiency. Okay, so sorry. Okay, so with this equation, if you put 10 Gbps once again, and you now consider noisy channel, like we have something like 20 dB of signal to noise ratio, which is not a very good channel situation, then the value that you get for B is 1.5 gigahertz. So the conditions are again Same, that means even if you consider noisy channels, you require much more, even more bandwidth. So again, our earlier arguments hold true that for a data rate of GBPS domain with a nominal SNR of 20 dB, you require a bandwidth of 1.5 gigahertz, and you require a center frequency in the gigahertz range. Now let us play with the equation a little bit. Like the Shannon-Hartley law that I have said can be written in this way, that is C equal to B log 2 1 plus SNR, but that is for CISO, like single input, single output. Well, when we have only one transmitter antenna and only have one receiver antenna, so this is called CISO, single input, single output. But we can have MISO, multiple input and single output. We can have MIMO, like multiple input and multiple output, where we have multiple antennas in the transmitter end, multiple antennas in the receiver end, and there can be communication between them. So the picture between shows three different cases: CISO, MISO, and MIMO. And the Shannon-Hartley law will be changed a little bit. How it will be changed? Well, if you have n cross n MIMO, then actually you can increase the capacity n times. So the Shannon-Hartley law for a MIMO case will be something like n into b into log 2 1 plus SNR. Now, actually, my goal in this lecture is to show how the millimeter wave actually affects all these three parameters. So capacity is the data rate, and the data rate depends on three parameters. One is the number of antennas, the second one is bandwidth, the third one is spectrum efficiency or signal to noise ratio. And I can show you that the millimeter wave is going to affect all three. How? Let us see one by one. Let us first target the bandwidth, which is probably very easy to understand. Well, with millimeter wave, as the center frequency goes up, the bandwidth that is available is also going up. So when the bandwidth goes up, the capacity goes up. So you can see that C is equal to N into B into log 2 1 plus SNR, and when B goes up, C goes up linearly, as simple as it is. So the picture below, the equation on the left-hand side, shows that the bandwidth that was available in 3GPP release 8 was 20 megahertz. That is something like 3G or advanced 3G. The bandwidth that we had in LTA, which is 3GPP release 10, that came in 2011, was 4G, and it had 100 megahertz. And the 5G new radio, which specification came in 2018, had a 800 megahertz bandwidth. Now, when we go from a center frequency of sub 6 gigahertz to 28 gigahertz, then we can see how much the data rate increases. And on the right hand side, with the table, we can show that the bandwidth can cause the data rate to go up from 1.35 to 40 Gbps, which is 30 times increase in the data rate. So that shows that if we go to the millimeter wave, we can afford more bandwidth, and more bandwidth ultimately results in more capacity, and the capacity means higher data rate, which people want. So this is only the one term that I have related bandwidth with capacity. In the next two slides, I will relate the other two terms. So the next thing that is also very easy to understand is to relate the number of antennas. Well, if we increase the number of antennas, then the capacity will increase. But we cannot go on increasing the number of antennas. We need to think about the real estate. Real estate means how many antennas you can put on the mobile phone or the device that you are going to use. Now, if you are going to use a 2x2 MIMO, the picture is shown here, then 4x4, 8x8, 16x16 massive MIMO, and then 64x64 massive MIMO, which is shown in the picture. If you want to know the current state of the art, I read an article which reported 128x128 real-time operation, and that has been developed by University of Bristol. So they are already there with 128x128 N cross and MIMO. What is the challenge, or how millimeter wave helps? If you are going to use 700 megahertz frequency, which was the frequency of 2G, then if you want to put 72 number of antennas on a mobile phone, you require a size of a door. So that means you require a mobile phone which is as big as a door, which is not feasible. But at 39 gigahertz, you can easily fit 72 antennas in a phone. So the takeaway message from this slide is millimeter wave realizes smaller antennas, And smaller antennas means we can put multiple antennas, and when we put multiple antennas in a mobile phone, the data rate will ultimately increase because the capacity is linearly dependent on the number of antennas in an N cross N MIMO. So this is how we have related the second parameter as well. Let us now go to the third parameter. The third parameter is the spectrum efficiency, which is log to 1 plus SNR, or signal to noise ratio. Now, why the spectrum efficiency is important? Well, you can see that the 4G LTE realized up to 256 constellation. Like if you consider QAM, let us look at the graph on the left hand side. In the left hand side, the graph shows the Shannon capacity and how with higher order modulation, like from QPSK to 1024 QAM, how we are reaching near the Shannon capacity. And the spectrum efficiency also increases as a result. Now in 4G LTE, the highest specification that we could support was 256 QAM. But in 5G new radio, which has been released 2 years back, can support up to 1024 QAM. So we are much more closer to the Shannon limit, and probably we are going to increase our spectrum efficiency. So the capacity reaches the Shannon limit at the high SNR. So that means with millimeter wave, we can have higher spectrum efficiency, and with higher spectrum efficiency, we can reach the Shannon capacity. So that means if we are going for millimeter wave, you are going to have more bandwidth, more number of antennas, higher spectrum efficiency, and the capacity is enhanced due to all these three factors. So this is why millimeter wave is so important, because millimeter wave is only the technology that probably can be used to reach gigabit per kind of data rate. It's not that the other technologies like massive MIMO are competitors, as I was saying earlier. The other technologies are is like complementary to it. Like when you can put a massive MIMO, of course you require massive MIMO support, like algorithms and so on, so that you can process data from the multiple antennas. So these technologies are complementary, and one requires another. It's not like they are competitors, and when one is implemented, other one will be left. No, not like that. So with these three things, I actually finish the fundamental discussion that why we need millimeter wave for higher data rate. Then I now move to something else, that is, what are some other advantages of millimeter wave? Like I was talking about small cell. Well, the picture below small cell, what I have shown here is that what is the coverage area per tower? Well, the LTE coverage area is quite big. The 5G new radio sub 6 gigahertz, which is not millimeter wave but still 5G, is probably even a bit smaller. But when we have 5G NR millimeter wave, then the coverage area is quite small. Now, when their coverage area is quite small, that means there is a very small area that has to be covered by the tower. Then you can make the tower even small. Actually, there is no tower at all. The tower will shrink and become a wireless router kind of thing, which you can simply attach on a wall. You can probably put on the table or something like that. So it is no longer going to be a tower at all. So that is one advantage. Like you don't have to make big towers. So you don't have to lease somebody else's area, pay the royalty fees and so on. You can just put it on anywhere, like in any public stand or top of the tree or somewhere you like. So that is one advantage. But more advantages is when you cover a small area, the number of users is lesser. So when the number of users are lesser per cell, you can realize higher data rate per user because the interferences will be less. So that is one advantage of using small cell. Then the other technology I want to discuss that is possible with millimeter wave is multi-user MIMO. Well, you are saying, Saidat was saying that we have beamforming. Yes, exactly. So in millimeter wave, you can direct the beams. So in lower frequencies, actually the antennas transmit in all possible directions. So it's not possible to steer the data to multiple devices. So what happens in single user MIMO is, suppose there are multiple users from a router. So the router serves node A, node B, node C in a sequential or round robin manner, and then again repeat it. Like it cannot serve all of them simultaneously. But if you have beamforming, then it can form a part of the beam towards user A, user B, and user C, all at the same time. So you can have multi-user MIMO by beamforming and pre-coding to serve multiple users simultaneously. So that is possible only with millimeter wave. That is not possible in lower frequency ranges. So with these discussions, actually, we have almost come to an end. Like what are like why millimeter wave is so important and what we can do with millimeter waves in 5G. And as you can see, the possibilities are endless, and there are a lot of domains which probably people can work on. I am not even trying to cover all of them. So as an after discussion of this whole theoretical things, let me only briefly describe what we are doing at NIT Durgapur. Like we are also involved in some part of the millimeter wave research, but as I said, millimeter wave is a very big domain. We are only catering only a small part. So what we do, well, we are interested in vehicular communication that is related to the millimeter wave communication, and we are interested in considering situations if the millimeter wave routers are put in public vehicles, then how the channels will behave. In the figure below here, we are showing that suppose we are putting a wireless access point, just like your router inside a bus, and that let the router be a millimeter wave router. So what advantage it can have? Well, suppose the bus is carrying 50 passengers and the bus is moving. So you had one tower here, you had another tower here, and when the bus moves from one tower to another tower, the handover from the tower to tower has to be carried out for all the 50 passengers together, because everybody is carrying one mobile. Probably people are carrying now 2 mobiles. So probably 100 such handovers are going to take place. How about that instead of these people, when they are within the bus, need not to be connected to the tower directly. Let them be connected to the access point inside the bus, and let that access point connect to the tower. So that access point can aggregate all the traffic from all the users and send it to the tower, and then probably take instructions from the tower and send it to all the customers. So when the tower changes, the communication is between tower and access point on the bus. The bus is having an antenna outside, and then probably can send it back to all the users. So actually, we did some real life measurements. Like this is the theoretical setting, but we only did not do theoretical things. We actually measured on a bus at 60 gigahertz, and then we have got some real results, like how the channel behave, because it is very important to know how the users experience the channel within the bus. Is it the case that the people who are in the front seat gets a very good coverage, and in the back seat probably they are not going to get good net? Because you see, people can tolerate bumps in a road, but probably people won't tolerate that the front person is going to have better internet than me in a bus. So that is not going to work simply. Fortunately, we found that the data rate and other things did not depend much on the position of the person. However, it depends a lot on the data rate, and it's like the frequency and other kind of things. So these are some preliminary things that we have done, and it was published last year in one of the IEEE journal, and this year also we are having some more publications like this. So this is one of the experimental work which we are trying to do in 5G millimeter wave, but at the same time we are also part of some standardization bodies. There is an IEEE standard which is being developed by IEEE APS, Antenna and Propagation Society, as well as Regular Technology Society, and we are working with NIST. NIST is something like equivalent of ISI in India. It is in USA, so it looks after the standards in USA. So it is we are collaborating with NIST USA. Then there is Fraunhofer Germany, and there is our team, and so on. And we are trying to develop a standard, worldwide IEEE standard, which will be ready by I think 2021 end or 2022 beginning, and that will be based on how this millimeter wave wireless channel sounder should be designed. Like if you are going to test a millimeter wave channel, what things you should follow. So that kind of thing we are trying to develop. We are also a part of the IEEE special interest group. Like we are part of the Communication Society, Radio Communication Committee, and they have a special interest group called Propagation Channels for 5G and Beyond. So we are happy that we are a part of that as well, and we are trying to gather as much information as we can from there and probably contribute in a worldwide manner. So we have almost come to the end of our presentation, and let me just summarize the main takeaways of today's topic. So the first thing that we discussed today is there is no ignoring that 5G is here. 5G is already here. 5G is there. Like 5G is in many countries, and probably 5G will be very soon in India as well. So be prepared. That is point number one. Point number two is 5G is going to promise high data rate, and truly really high data rate if people want in 5G, because the 5G that is being rolled out are not always having the high data rate. So if you want to make your data rate even higher, you have to use millimeter wave. But at the same time, the third point says that millimeter wave brings new challenges. Well, if you are going to use millimeter wave, you are bound to have a lot of difficulties at the beginning. You have difficulties in manufacturing the antennas, you have difficulties in manufacturing the VLSI hardware, and of course there are issues with propagation. Like said that there is indoor, Nabin said that there is indoor and outdoor kind of problem. Probably the coverage is better indoor, probably the coverage might be not so good in outdoor. So you have to tackle those challenges as well. But the good news is the fourth point, that millimeter wave not only brings challenges, it also brings new opportunities which were not possible earlier. Like if you want to implement massive MIMO, well, theoretically massive MIMO can be implemented with other frequencies as well, but they require such a large antenna structure that probably is not practical. But if you use millimeter wave, then the antennas become small, and then you can fit a lot of antennas together, and then you can have this massive MIMO structure. Then you can have MU MIMO, which is multi-user MIMO, where you can serve multiple users at the same time with MIMO. And then there is another concept called small cell, which is with millimeter wave, as the attenuation is not very big, so you can contain it into a smaller range. So this is like the nutshell, and I just try to finish that it is high time that you start your research on the beyond 5th generation or 6th generation. Like 5G is already there, so millimeter wave and the future things are going to be coming in B5G or in 6G. So let us be prepared and let us start researching on that. So thank you very much for listening to this. I'll just, before concluding, I'll just try to thank ACRB. Like we have got a project from Science and Engineering Research Board, and this lecture is also a part of their social responsibility policy. So I'd like to thank SARB for providing money to our research. I'll also like to thank my institute, NIT Durgapur, for granting me permission to give this lecture. And finally, last but not the least, I would like to thank Kakatiya University and Professor Hari Krishna to give me an opportunity to speak in such an occasion. So if you have any queries, this is my web address. Actually, the web address is quite big, so I have shortened it out with tiny URL. And you can also email me if you want. So thank you for listening.
Yeah, it's a very nice presentation, sir. I first of all, I thank you, sir. Besides a small interest that to reach the 5G communication to the larger extent, and your research and your contributions are extremely good, sir. In spite of your busy schedule, sir, you are taken this 1.5 hour time to reach out our participants. Thank you very much.
Thank
sir.
you. Thank you.
Yeah, if at all any participants, if you want to speak with the sir, please speak, and otherwise we'll close the session. Okay, sir. Once again, thank you very much, sir. Thank you very much.
The pleasure is all mine. Thank you.
Yeah. So next session will be started in few minutes. I'll start the next link. Thank you.